dysrhodium, and its empty space, and its empty hole will trap the electron. Eventually, the electron will jump back down and emit light. And the nice thing about emitting light, anything that can emit light, there are devices, photo-stimulable plates that can, and ways in which you can turn light, you can turn it into electricity. Okay, it's been used for forever. Okay, image intensifiers, that's how they work. It's used all over the industry. It's used that way. All right, so that's good. Now, the latent image will lose about 25% of its energy, okay, in about 8 hours. So if you don't develop it right away, okay, or if you don't develop it within, you know, a good amount of time, you will start losing. Some of those electrons will start jumping back out, going back out, okay, and then the to create the manifest image will be more difficult, and so it needs to be, you know, within the first. It is recommended within the first hour after the exposure that you process CR plates. So it is important to process the cassette shortly after exposure, 1-2 hours max, because you know you're going to start losing energy there. The image acquisition. So the imaging plates, the imaging cassettes, also known as film cassettes, can be used tabletop or with a grid. So that's the nice thing about CR plates. In many places, before they went into DR, this is typically the first step that places will take if they want to go digital. From film, this is the first step because it's easier for the technologists to adapt, because this is just like a cassette. You can take it to portables, you can put them in the bucky, you can put them in a grid, you can put a grid on top of it. They work just like regular cassettes did. And so you don't have to do a whole conversion of your system. Okay, because when you have a DR system, you have to change everything. Okay, not only the X-ray table. I mean the bucky, no bucky anymore, right? The two, you have to change everything, and so it's a big investment. It's a huge investment. You're talking when you're going to a DR system, good DR systems, you know, they're going to be valued close to $1 million. It's a huge investment. So hospitals can pay that, but you know, if you have a small clinic, you might not be able to do that. So typically doctors, that's what they have done, and even hospitals did that before they went DR, fully DR. They start CR, okay, to you know, just to get them going in the digital era. Okay, so many benefits. Rules of positioning remain the same, just like what you did with cassettes. Okay, and so it was easier too. This is another side note. It was difficult for technologists when this technology came common. You know, if I go back 6-7 years in our program, you should have seen it was crazy, because that was the time when our hospitals were changing to digital systems, and some of the techs were using some really crazy techniques, and it was just, and especially those that went straight into DR. So I think it's easier. It was easier for techs because everything pretty much remained the same. You still have to be careful about techniques, but everything else was the same, and so this helped a lot. One thing to recognize too with imaging plates, with CR imaging plates, is that they have a wider latitude when compared to film and screen radiography. Wider latitude for what? What is that saying?
Density, highlights, shadows.
Contrast. Yeah, the densities that you can show an infinite number. I mean, the system is capable of showing an infinite number of shades of gray. Now, your screen, listen here carefully, don't take this wrong. Your screen might not be able to display it, but the system is able to acquire a lot more densities than film did. Okay? So it's something to keep in mind that it has a wider latitude compared to film and screen. All right, so it is the responsibility of the radiographer to select proper technical factors. Chronic overexposure should be avoided. It is unethical. Okay, it's unethical. You can't do that. Okay, ethical principles. Okay, I mean, I told you this before. I told you this in Radt430. I told you this in Radt410. You should look at radiation as something that is prescribed by a physician, just in the same way as a drug is prescribed by a physician. It can be harmful to the patient, okay? And it is, especially if you know, okay? If you know that you're overexposing patients, people, okay? You need to report that so they can look at the equipment. If you don't report that, it is unethical. You're just as fault as everybody else for not doing anything about it. Okay? Radiation can do damage. Okay? We might not see it. We might not see it in the 5, 10, 15 years, but it could, you can inflict damage on the patient. So it's something to keep in mind. The Alera concept has to be always there. Always there. Okay? Why? Because these systems offer you the opportunity to overexpose patients, and still the images look perfect. That's what is so deceiving, that your image will look beautiful even though you are overexposing a patient. You know you can overexpose a patient by 400%. 400, I'm not talking 100%, 400%. A patient can be overexposed and the image still looks fine. I mean, if someone is really overexposing more than 200% of patient, that person doesn't belong in this field. The patient doesn't understand any concepts of anything that we're trying to do here. But it's possible. Can you underexpose patients? Yeah, you can go about 60% underexpose a patient, and still the image still will look somewhat okay. Reading the CR data. Okay, so all of that, what I have said until that picture I had of the X-ray in the cup and then coming back down, everything I said was a little parenthesis to just kind of expand on CR plates. Now we go back to that section. Okay, so what happens when the electrons are in the cup, are in the room, and they come back? What are you going to do with that light? Okay. So that's what we're going to do. So those trapped electrons are freed. Okay, how are they freed? Okay, because if you leave them alone, they're going to start one by one, they're going to start jumping back, but then you're not going to be able to capture light that way. I mean, if you have one electron jumping back, are you going to see that light? It's just one light photon. You're not going to see it. Okay, so you need all of them. The idea is to have all of them or the majority jumping at the same time. Okay, and so that's what we're going to do here. So the imaging plate is scanned by a finely focused neon helium laser beam. So you use a laser, and it has to be of this type, neon helium. Okay, you can get lasers from different elements, but for the purposes that we're using it here, because they emit the right wavelength that you want, the right energy that you want for the electron to jump back out. Okay. Raster. Raster, what raster means? Right? This is a point. A raster is a line. It's going to go like this. Okay. Make sense? Raster is called, for example, have you seen tractors working in the fields? Okay, what they are pulling back when they are cracking the ground, that's a raster. Okay, so in that pattern, that's how the laser is going to move.
Yeah, raster is just a straight line.
Yeah, some of you never work on the fields. You know what I'm talking about. Yes?
So it's more like a rake and not a squeegee, right?
No, the raster, not in that sense that it's separated. It is more like a squeegee, but it's going in a straight line. Make sense? So that's how the beam is gonna move. So it's not gonna move like this. This is a beam, this is a laser, right? But it's a point laser. Okay? So it's gonna be, instead of being like this, it's gonna be a line. And that line is gonna move like that, in one pattern. Make sense? All right, so electrons return to the lower state, okay? Because you're giving them energy, okay? That energy that the laser is giving them, now they can jump back. Whoop. Okay? Yeah? Okay. Make sure. So, when do if I have, and I told you this 3 times already, let's see. Okay, you have this here, electron here, and electron here. Which one of these electrons has more energy, this one or this one?
More binding energy or just
Outer shell.
Energy.
outer shell?
Okay, so this one, right?
Yeah.
Alright. Good. So, for this guy to jump in here, he needs to what? You will release energy, right? Jump here. Alright? But they are not just gonna jump. Okay, in some cases they do it automatically. In this case they don't. You need to get them going. Remember I told you that before, you need to kind of give them a push. And that's what the laser is doing. The laser is just saying, jump. Okay, and then they jump. So the electrons return to the lower energy state. That's what I'm saying, return to the lower energy state. The photostimulable luminescence happens now. Okay, why is it photostimulable? Because with the laser, it's stimulating them to create the light. Okay, so the lasers stimulate them, okay, and then they release this light. And then they emit this light. This blue, purple kind of light. Colleen?
Yes.
Are we good?
Yeah.
All right.
Do you think Carl?
Checking. Yes.
Do you think Carlton or Bouchon explains this better?
They both
like,
do.
They both
do
do.
a great job.
Okay.
Yeah. They do. In this case, they both did a great job. I don't know who was writing this chapter for them, but they did a great job.
Is this a word on or?
Both. They both have both areas are really good. And they pretty much explain the same thing. Yeah.
What was the significance of like inside the CR plate? It was like light blue. Does that have any significance?
This is what I've been saying. So when you expose the film, okay, you're done, and then you will bring it into a reader. And that's what I'm describing right now. You put it in there. This thing is open. Whoop,
Yeah.
and the plate, the light plate, is run through a laser light. The light is exposed there. And then in the process of being exposed with the laser light, they emit their own light.
Okay.
This blue purple light has been emitted. And now you can measure that light, and you can turn it into an electrical signal. That's what's gonna happen. That make sense?
Yeah.
So we have this, okay, the light is captured by a PM or photomultiplier tube. The photomultiplier tube captures that light and turns that light, eventually we're going to see in just a second, that is turned into an electrical signal. Sarah, are we okay?
Yeah.
Yeah?
Sorry.
All right, no, that's okay.
Hi.
Yeah, all right. Yeah. I know I've been saying a lot, guys, and probably a lot of new stuff. So, but does it make sense?
Yeah.
Yeah.
So,
Yeah, Monique? Good? All right. All right, so, huh?
For the non-helium, you said it was the right wavelength.
Say that again?
Non-helium laser emits the right wavelength, like that.
If the wavelength is in the same order that you need to release the electrons, they're gonna come back down. But
Is there like
all
a fixed one?
manufacturers use the neon helium laser. All of them.
So it's set
Is that what
by
you're
the
asking me?
non-helium and not the wavelength. That's why they
Say
use
that
the
again?
same. Is it fixed? So it's fixed. Because
What is fixed?
the
Can you ask me the question from the beginning?
just
I'm sorry
like
to interrupt.
it's okay. The neon helium, they use that to produce the right wavelength that is fixed, or the wavelength, or is it the other way around?
The neon helium, they're gases, right? Okay, and they emit this very specific type of light. Okay, they can emit visible light, but they also emit laser light. Okay, depending on how much intensity you're beaming at them. All right, the laser light that they emit is not red like this. It was actually kind of reddish like this, deeper than this. Okay, but it has the perfect wavelength. That wavelength is what is needed to bring this guy down here. If the wavelength doesn't correspond, when I say wavelength, what am I saying?
Like
The light wave.
Energy. The energy. If the energy is not the same, okay, or is not what is required here, this is not gonna jump. Now, were you asking me if this light and the laser had the same wavelength?
Like, is
Or
it a
is
set
it,
number?
Yeah, is it fixed?
Which is fixed?
The wavelength.
The
Like, is it
wavelength.
a
Which one?
specific?
This one or the
The,
laser?
the outside one, which needs to jump back.
Yeah, that's what I'm saying. Is it the laser wavelength? This wavelength
Yeah.
Yes.
Yeah, that one.
is
Yeah.
fixed.
It's
Yes,
fixed.
this fixed is 680 nanometers. or
And that's the
something like that.
neon helium, is that one the neon helium that's fixed? Okay.
Yeah. And I can't remember what it is. It's
We don't have to know.
It's
that.
like 680 or something. Yeah, you don't need to. Okay. All right? Everybody? Okay, good. So the photomultiplier will capture this light. This is like something capturing all this light. It's like a sack of things, and you're putting all the light photons are putting here, and then you through a process, okay, and on the other side of the sack, you end up with electrons. So you start with light photons, and then you create electrons. Okay, all photomultipliers. Okay, so this slide is the last one, so hang in here. So the photomultiplier tubes convert light to an analog electrical signal. Okay, still is not a digital signal, it's an analog signal. Okay, so it's an electrical current. That's what you have. It's a whole bunch of electrons. Okay, the analog electrical signal, okay, is sent to an analog digital converter. Okay, an ADC. The ADC will break this. Remember, analog signal is a continuous signal. It's non-stop. Say if you're, there are no breaks. It's just one full single signal. Okay, digital systems. And so what? So we send this analog signal. So you send this signal to the ADC. The ADC sends the signal there to a computer for additional processing. Okay, but the ADC, what it's going to do when you send the signal is going to split it. It's going to, so instead of being a long, extensive signal, okay, you split it into pieces. This is easier for the computer to analyze because it can go and analyze one by one. And that's what the ADC is doing. Okay? Make sense?
Yes.
All right. So when someone asks you, a digital system has, my digital sound, for example, has more information than your analog sound. Is that true? No. It's not. It's just what happens with analog. It's just that we don't have the devices to look at all that information and process it. in an analog signal, you contain a lot more information, a lot more. You know, we're gonna get to the day where we can read and analyze analog signals, and we're gonna hear all the crisp sounds and everything. It's just that at this point in time, we don't have the means to read it completely. We read portions of it. That's when you're listening to a old sound in a vinyl, for example. You know, it doesn't sound very good. Bunch of cracks and stuff because you cannot read everything that is there. With digital, you're reading every little piece. And that's why it sounds better. We okay? All right. You really need to read this section. All right, before Monday. Read it so it'll become easier. Okay. Any questions before you leave? I'm asking everybody, not just you, Karen. He's looking at me. Not just you. Everybody has any questions? No? All right. Have a nice weekend.